All right, so the first few problems that we're going to work on have to do with average rate of change and finding the average rate of change. So to sort of illustrate what the average rate of change is, we can take a look. At this graph, and essentially this graph shows a graph of a function f of x, and we can see 2 points denoted on this graph. So the first point number 1, has coordinates x1 and y1, and the second point has coordinates x2 and y2. So the average rate of change is nothing more than just the slope of the line that connects the 2 points, right? So the average rate of change is defined as the change in the y value, right? So the vertical rise or fall, divided by the horizontal run. You may have heard of the term rise over run. So what that means is you take the difference between the y coordinates, namely y2 minus y1, and you divide it by the difference between the x coordinates, so x2 minus x1. All right, so the first example that we're going to take a look at has to do with finding the average rate of change of the volume of a balloon. So the problem is problem number 2 here, and it reads, Mickey is blowing up a spherical balloon. What is the average rate of change of the volume of the balloon with respect to the radius of the balloon as the radius increases from 4 inches to 7 inches? So in this example, what we have is a spherical balloon. So we can say maybe this is just our balloon here. And our balloon has a radius of 4 inches. But then the volume of the balloon increases to 7 inches. Right? So to solve this problem, we need to define what our y values are and what our x values are. Since we're talking about the volume of a balloon, that means that our y value is going to represent the volume. So we're going to write the equation for the volume of a sphere, which is v equals 4/3 pi r cubed. Now, the problem says we want the average rate of change of the volume of the balloon with respect to the radius, which means that r is going to play the role of our x value, as we showed in the example up here. So since we're calculating this average rate, we want the change in y divided by the change in x. In other words, what we want to do is calculate the volume when the radius was 4 inches, right? So this is 4 inches. And then calculate the volume when the radius is 7 inches. So our first volume is going to be for 4 inches, second volume is going to be for 7 inches. And then what we want to do is we want to take a difference between those volumes, right? So we can write this as v of 4. So v when r is equal to 4 is equal to 4/3 pi times 4 cubed. Okay, so this gives us a value of 256 pi divided by 3. Now we're going to calculate the volume at 7 inches. So this is 4/3 pi 7 cubed. So this gives us a value of 1,372 times pi divided by 3. Okay, so since we want to get the average rate, we need to figure out what the change in volume is. So our change in volume is equal to v at 7 minus v at 4. Notice that we always take our change to be the final value minus the initial value. We initially had a volume corresponding to 4 inches, and then in the final scenario we had a volume corresponding to 7 inches. So our change in volume is going to be the 1372 pi over 3 minus the 256 pi over 3. So when you take the difference between those two numbers, you end up with 372 pi. So now that we have the change in volume, what we want to do is get the change in the radius. So our change in radius is 7 inches minus 4 inches. So this gives us 3 inches, which means the average rate of change for the volume of the balloon is 372 pi divided by 3. We can round it to 1 decimal place. This comes out to be 389.6. And our unit will be in cubic inches per unit inch. Right, so if we go back to the problem, right, the answer that we got here is answer choice B.